Okay, this one's about finding inverses, which is pretty easy because you guys have already done inverses in the big general functions unit. All right, and remember finding inverses. One way to think about inverses is it's the same thing as finding the reflection over the line y equals x. Another way to think about inverses, you can also find inverses by switching x's and y's and solving for y. Okay, so this first one, just graph this as a line. So I have an intercept of 1, and then I have a slope of -2. So it's going to look something like this. Let me pause and use the other tools for this that take a long time. You don't want to watch that. The straightest line I've ever drawn in my life. All right, and then add x equals -y. X equals y is a dotted line. So it's something like this. Well, the y equals x line is somewhere around here. This is pretty rough, but yeah, it's hard to draw this straight on here. Reflecting these points across this line, that point would go right there. Let's do another one. -1, 3 would be like -1 this way and 3 this way. I think is gonna be like that. And this slope should look like a different version of 2. In fact, it's -1/2. Let me draw that in more straight. Here, give me a second. Okay, I'm off by a little bit, but I think you get the idea that that's the reflection of those two things. Okay, and then find it algebraically. Okay, so algebraically, we want to rewrite this like pretending that this was actually y here, y equals -2x plus 1, and then switch the x and y. So we're looking at x equals -2y plus 1. Solve this for y. Divide by -2. And I get what I have there as that blue line. That's an equal sign. I have an intercept of +1/2 and a slope of -1/2. All right, now with parabolas, this is a little more interesting. This is a parabola that has some points on it. Let me plop those in. Okay, those are all the coordinates of the points I see on the graph. Oops, that should, oh no, that's right. Okay, and then it says switch x and y. So let me write those in the opposite order. Like so, and so if there's to be an inverse, these would be the coordinates that would be on the inverse of the thing, or inverse of this parabola. Sketch the inverse on the same grid. Okay, so let me, I'll do this before, like I did before. I'll change this to blue. So I want to do this. Boom, so magically, first of all, they're all blue. That's nice. Oh, of course, this was already blue, and I'm going to make another blue on top of here. Well, imagine that one was red. This would have been really slick. Okay, let me plop those in there as coordinates. Again, it's a little bit of an unsteady hand when I try to do this on here. But anyway, you can see if I put these coordinates into this graph, I get this kind of sideways parabola. If you look at the original parabola and imagine reflecting across this line x equals y, it still kind of does what we expect it to do. Then the big question, is that thing a function? This new kind of shaky, thin blue line that I drew, not as pixelated as the first one. Anyway, no, it's clearly not a function because there's all of these values here that have the same x value repeated that lead to different y values. And that's like the definition of not a function because each x can only lead to one y. Oh, I forgot this thing. Could we have found this inverse algebraically? Yes, we could have. Algebraically finding an inverse means, oh, I guess I would have need the equation, which I don't have. But finding the inverse algebraically would mean switching the x and y in an equation. If I make an equation, we'll do this again later, but if I make an equation, switch x and y and solve for that, yes, I should have gotten something like this. This would involve a y squared, or a quadratic involving y, and that does happen. It just turns out that it won't be, just like this, if it's going to end up with the same graph, it won't be a function in x. Okay, so is the inverse of a parabola ever a function? Well, no. If you flip a parabola over that line x equals y, it's always going to be some kind of sideways parabola. It might open left, it might open right, but it's not going to be a function. And that's a problem. And it all stems from the fact that in parabolas, you've got the same y value repeating for different x values in the original, which is fine in the original for a function, but that's because of the symmetry in the nature of a parabola. That's always going to happen. But then when we flip them and go kind of this way, we flip the x and y column, we're going to have x's repeat that go to different y values, and that makes it not a function. Okay, so we got to do something about that. So the thing that they talk about here is restricting the domain. So when you had to solve this before, we called this the inverse, but this is a little bit weird because this symbol here, this radical x, this implies that we're only talking about half the parabola, or it implies we're only talking about the positive version of the square root of x. This is not the entire solution of x squared. It's just, this is the one we're going to use to make this work out as a function. Implied in this notation is when you use the radical symbol by itself, you're implying that you mean just the positive square root of x, even though there are two. But they do that for a couple of reasons, one of which is it makes it so that thing will be a function and it won't be ambiguous. Okay, I think I've just basically said all this stuff here. So we have to restrict the domain. So in other words, they're saying this only is going to be possible if we only think about half the parabola at a time. Let's get a little more specific. Consider the domain, or sorry, consider the function of this. Graph the function first. Let me do that. Okay, that turned out better than the first one. Decide which half of the parabola you will focus on, the left half or the right half. Let's do the right half just because it's a little bit easier. Restrict the domain f of x squared minus 2, so you only look at half the parabola. Okay, I really only want to focus on this half over here. I kind of want to like kind of forget that this exists. Can I just do this for you? Let's not pretend that that exists, and let's only talk about inverting this side that's in the yellow. So to do that, I have to think about domain being different. What's the domain of that part over there? And this is the way to do this. The domain I really care about, and I'll do it in interval form. And I can include the 0 because that's not going to cause a problem. From 0 to infinity is the part that I care about, if it's going to be the part that's in yellow. Graph the inverse of that now. Now that the domain has been restricted, I can graph the inverse of this if I've restricted the domain of this to be only 0 and up. And I'll do the inverse in a different color. So this 0, negative 2 is going to go here. And I should have a sideways parabola that looks something like this. Something like that. Is it there? No, I think it's here. Okay, let me draw that. And that is the inverse of just the part that's in yellow. If I'd start flipping around the part that's also in gray, then I would have had things that aren't a function, but just this blue thing by itself is a function and it's perfectly fine. Determine the inverse this way. Okay, now I think maybe this domain restriction will make a little more sense. So it was originally that y equals blah, blah, blah. I'll do it in blue so you can tell I'm still talking about the same function. When I flip those, yeah, now it turns blue. And I get x equals y squared minus 2. Okay, so I can do this. X plus 2 equals y squared. I do the square root. Now when I do the square root of this, I'm only doing the square root where x is going to be positive. So x plus 2 being a square root and being positive is not going to be a problem. I don't have to worry about this ever being less than 0. So that's all kind of nice. And I'm done. This is the only one I care about. And I was restricting this to be the positive domain, so I am already considering this to be the positive square root of x plus 2. Okay, graph this one. I'll do that. Okay, something like that. Restrict the domain so that's 1 to 1. Again, I like doing the right half. You can kind of do whichever half you want, but let's start from -3 and we'll go up to infinity. All right, graph the other half on the same grid, or sorry, graph the inverse on the same grid. So this point here at -3, 0 is going to go down here 3. I'm just thinking about flipping over the line. It's going to look something like that. And this parabola is, if it's the positive half there, make my meatballs a little fatter here. It's going to be the standard size parabola. It's just going to be going this way. 5, 6, 7, 8, 9, something like this. Okay, I'll finish graphing that. And again, that should remind you of, okay, that's been that half wing of the parabola flipped over this line here, y equals x. Determine that algebraically. So I would have x equals y plus 3 squared. I can square root both sides now. One nice thing about just thinking about the positive half of all those is, you know, you're going to have to deal with the positive part of this. So that's kind of nice. And then all I have to do is, whoops, what am I doing? All I have to do is subtract 3 on both sides, and I'll get this. Okay. All right, one more graph, or another graph. Let's do this. Okay, I graphed that one. Let's restrict this so that it's 1 to 1, or basically that it's invertible. We'll go from we'll go from 4 to infinity. Graph the inverse on the same grid. Okay, again, I'm thinking, take this. I think the easiest way to do this is to just think about inverting the points first. This is at 3, 1, so 1, 3 kind of goes there. This one at 4, -1 is going to go 4 up here and 1 backwards, something like that. And then just draw the same picture, just sideways. Okay, sorry, I almost made a grave mistake there. Forgot I'm only doing half the parabola. I'm only doing this upper half. So if you always just do the right half of the parabola, you're always going to do the half of the parabola in the inverse that just kind of starts over here and kind of points upward. It's going to be the upper half of the sideways one. And let's do the inverse. This is going to be x equals 2y minus 4 plus 1. Solve that for y. Okay, this one turns out a little bit weirder. And you could write this a different way. I could have gone x plus 1 over 2 and done a square root and gotten it out of the radical. But that will be fine. that should give you the same thing. And you could check these by graphing them on your calculator if you're not doing the test, of course. Okay, and just as before, they have this verifying inverses by checking the composition way. Is it that you can compose f of g of x should be x and g of f of x should be x as well? Okay, so let's do this with quadratics. It's slightly weird because of the restricted domain. Okay, so f of g of x in this case is like saying f of square root of x minus 4. We put that into the f function, it becomes that thing squared plus 4. Well, I square that, that's pretty nice. That's just x, whoops. Oh, can I do that quickly? Oh, I can, okay. That's just x minus 4 plus 4, which miraculously turns out to be x. Okay, great. Then we have to also check g of f of x. Getting better at fixing my mistakes. G of f of x, and that would be g of this thing, x squared plus 4, which is like putting that into the g function. So this would be x squared plus 4 minus 4, which is the square root of x squared, which if we have our restricted domain, everybody's happy. It is just x. This is a great big yes for this one. Okay, we'll do the same thing with this. F of g of x would be like putting this function into this shape. So square root of, instead of x, I'm going to write this thing, 2x squared plus 1, or sorry, minus 1 plus 1 divided by 2. Maybe I should say what I'm doing. This is f of g, and that is 2x squared over 2 under square root. 2's cancel, and I'm good. And then in g of f of x, I have, these equal signs aren't looking nice, sorry. 2 times this other thing, square root minus 1, that's in the g shape. I'm just putting, instead of x here, I'm using that guy over there. Square that, I get this, which is 2's cancel, which is x. So great. And last one, find the inverse of this and by first restricting the domain. Okay, the only way I know how to do this, sort of the safest and fastest way I know how to do this, is still to think about the graph first. Okay, so this graph has a vertex at 3, -2, and the parabola is going to look something like this. Oh, sorry, it's going to open down. That's fine. It's going to be 3, -2, and it's going to open down. If I just want this part of the parabola, this was 3, I want the domain where we're talking about from 3 to infinity. Okay, so only on that domain. I'm going to reverse. Oh, and I've been doing this in blue all day when I reverse, so I'm going to keep doing that. X equals negative y minus 3 squared plus 2. Try to do you a favor here and save you some time. Okay, so I'm subtracting 2 on each side, subtracting 2 on each side, then I'll multiply by -1. Then I will take the, take the square root on both sides, and then all there's left to do is add 3. Okay, and there we go. Yep, they're going to look like this. They're going to have the square root every time. Okay, and then you have to go on now to the 2.5 video, which is in 2 parts. Sorry about that. But I'll tell you right now, when you start the 2.5 video, because of what I gave you in notes, you can start it right at 3 minutes and 30 seconds. Okay, that should save some time. Okay, bye.